model, as I said, it's the topic of your next homework. It's called naive Bayes. So it's mainly a simple probabilistic modeling as you're gonna discuss. So with 1R, what we did so far is that we start with one attribute, right? And then we try to choose the best of them, right? So we calculate the errors and we pick the one that had the lowest error. That's how we did 1R. So now they thought, can we do something completely the opposite? Now let's take all the attributes, not just one, and then do one very important assumption. In order for this whole thing to work, you'll have to do two things. You have to assume that all your attributes are equally important, okay? So all of them have the same weight. And you'll have to assume that all your attributes are independent, okay? Equally independent, completely. So, which means that knowing the value of one attribute will never make you know the value of another attribute. They're completely independent. So these two assumptions are crucial if you want to use this method, which is a probabilistic method. Keep in mind that this assumption that I just said, it's almost never true. In real world, it's almost never true. But it turns out that when they did this analysis of this model, it surprisingly works when you do this assumption. That's why they kept it in there in the books. But this assumption is almost never correct, okay? But anyway, let's assume that it is correct. So, it's easy, it's fast, and it's called naive Bayes. Let's discover why it's called the naive Bayes model. So always staying in the weather data set. You like it so far, the weather data set? It's your best friend? Okay, so let's use the same data set. So the way you do naive Bayes, so this is the raw data set, okay? This is what it looks like, a table. Now, if I want to apply naive Bayes, I would create this table. I call it statistics table, just me. So what you do is you have two parts in the table. So you put all your attributes, okay? So we have outlook, temperature, humidity, windy, and play, okay? Those are your columns. And then the rows will be the different values for each attribute, okay? For instance, for outlook, we have sunny, overcast, and rainy, okay? Now I do the frequency count again, okay? Wait. So sunny, yes, you go to your database, tell me how many sunny, and yes, we have. You just do the count from outlook equals sunny and play, yes. 2, okay. How many overcast, yes. 4. Are you counting or just reading it from you? Okay, it makes sense to just read it. All right, so and so on. And then the second part of your table will have, so before I show you the second part, the last column is the class itself, which is play. You do the count, how many yeses and how many nos. So we have 9 yeses and 5 nos, okay? That's what I have in my database. So now the second part is I say, how many, what's the probability of having yes, sunny, and yes. So as we said, the count is 2. And how many yeses I have? 9. So the probability of having a day that's sunny and the play is yes is 2 over 9. Again, you do the same thing for sunny, no. So how many sunny no I have? I have 3 days. And how many no's overall I have in my data set? I have 5. So the probability is 3 over 5, and so on, okay? Someone had a question.
Oh, I have a question.
Okay, wait, let him. Who was first? I don't remember. You had a question?
Yes,
okay.
So in this case, this model itself is actually different from the R model due to the fact that we're actually organizing the data in the table instead of organizing it in a...
No, it's not the representation that's the difference. The difference is you are now assigning probabilities. You're not just doing the count, but you're also assigning the probabilities based on the independence assumption, okay? Since they are all dependent and equal, then we can do this simple probability.
I was going to ask, it's the probability based that it is, like, given that it is yes or given that it is no?
Yes, so you have two classes here. Okay, so now that we did the count and we assigned probabilities, what do we do? So keep in mind that the last thing that I did there, the probability of yes and no, we call those overall likelihoods, okay?
Oh.
So what do we do now? I gave you a data set, a training set, and you created this table, the statistics table. Now I will give you an evidence. And the evidence in this case is going to be a new day, okay? And your job is to tell me, is it play yes or no? Give me the class, okay? So that's what the model is about. We're doing classification. So we have a database, we started with it, then we have an evidence, a new day. So I gave you this new day where outlook is sunny, cool, temperature cool, humidity high, windy true. And the goal, as I said, is to know the class. So what we do first is we calculate the likelihood of the two classes. How do we do that? So as we said, we treat those 5 attributes as equally important, okay? Which means that we can do the multiplication of those probabilities, okay? So for outlook equals sunny and yes, what was the probability? 2/9. For humidity high and class yes, what was the probability? 3/9. And then humidity, temperature cool through 3/9. Humidity high, 3/9. Windy true, 3/9. So you multiply them, and at the end you also multiply the likelihood, the overall likelihood of the class, which is in this case the likelihood, the overall likelihood of class yes, which is 9/14, okay? So now I have the likelihood of class yes equals 0.0053. Now I haven't decided which class yet. What I have to do is do the same thing for class no and then compare. So let's do the same thing for no. So again, sunny and class no is 3/5. Humid temperature cool and class no.
1/5.
Yes, and so on. So you do the same thing, and then you multiply by the overall likelihood of class no, which is 5/40. This will give you 0.0206. So the values of the calculated likelihood shows that for this new day, class no is more likely than class yes. So we can turn these numbers into probabilities via normalizing them so that they sum to 1. So the probability of class yes will be the likelihood of class yes over the sum of likelihood of yes plus likelihood of no. And we do the same to get the probability of class no, and then the final outcome or the final class chosen will be the one that has the highest probability, which is in this case class no, with a probability of 0.795 or 0.8. So what we just introduced is based on something called the Bayes rule of conditional probability. Bayes rule. This is basically what the Bayes rule looks like. In probability, if I ask the probability of H given E. So H, we call it a hypothesis. So the probability of a hypothesis given an event, so E is an event. In our case, the event was that new day, okay? So the probability of a hypothesis given an event equal to the probability of that event given the hypothesis times the probability of the hypothesis over the probability of the event. So this equation is called the Bayes So now we know why do we call it a naive Bayes algorithm. Bayes because it's based on the Bayes rule, okay? And naive because it makes that naive assumption that the attributes are independent, okay? So naive Bayes, it makes a naive assumption. So look at what we just did, which is the probability of calculating yes given an evidence, and the evidence was that new day. So we did the same thing here. We multiplied all the fractions of probabilities because we assume they're equally important, and then at the end we put the overall likelihood. So it's the same thing.
So now you can see that we did apply the Bayes rule to calculate the likelihood to classify the new day, which is the evidence. So given an evidence, we calculated the probability of both classes yes and no, and then we chose the one that has the highest probability. So to get the probability of class yes given this evidence, which is the new day, we calculate the probability of outlook equals sunny, right, and class yes, and then times the probability of temperature equal cool given class yes, and then the probability of humidity equal high given class yes, and the probability of windy equal chill given class yes, and then we multiplied by the overall likelihood P of yes, which is also called the prior probability. Why is it called prior? Because we calculated this probability without having any evidence. So this was a prior knowledge that we had from our training data without knowing anything about the new evidence. So P of yes is the prior probability. And then we multiply everything here. So don't worry about the P of the evidence. It will cancel out when we are normalizing these two terms into one final probability of class yes, and the final probability for class no. So if one particular attribute's value does not show up in the training set in conjunction with every class value, then we end up having a problem called the zero frequency problem. So if, for instance, humidity equal high only it only occurs with class no, then we're going to end up having a probability of 0 for P humidity equal high given yes. If we have that, then the entire posteriori probability, which is P of yes given E, will be 0 as well, because remember, it's a multiplication. So how can we solve this problem? There is one remedy called the Laplace estimator. Okay, so how can we apply the Laplace estimator? This is again an example with the weather data set. And this is the original count that we had per attribute value. So we see that we got a problem here with overcast and class no. It has a frequency count of 0. So to remedy that, we need to add 1 to all these value counts for all the attributes. So this means that instead of 2, we're going to have 3. Instead of 4, we're going to have 5. Instead of 3, we're going to have 2. Therefore, the probability of sunny yes will be 3 over, it's not 9 anymore, but the total here is 12. So 3 over 12. And then here, instead of 4 over 9, it's 5 over 12. And here it's 2 over 12, right? So the prior knowledge or the prior probability should not be touched. We do not add +1 to the prior knowledge, because this is like our prior knowledge coming from the training data set, and it has nothing to do with the new evidence that we are going to be presented with, so we do not touch the prior probability. So how do naive Bayes deal with having evidence that has missing attributes with missing values? For instance, here Outlook has a missing value, so we don't know what's the actual value for the attribute Outlook. So one simple way that naive Bayes deals with missing values is to not include it at all in the frequency count, which means we're just gonna ignore this attribute when we are doing the calculation. Therefore, the likelihood of yes, in the likelihood of yes, we're just considering the temperature cool, the humidity high, the windy true, and the prior knowledge of the class. So what we learned about so far applies in the case that we have nominal attributes. So what shall we do if we are presented with a data set that has numeric attributes? So naive Bayes in this case will make this assumption that the data has a normal or Gaussian distribution, right? And then what we need to do is to calculate something called the probability density function, okay, for the normal distribution, which is equal to this. So this is the density function. To calculate this, we're going to need the standard deviation and the mean of the training data. So we calculate the average, the sample mean, and the sample standard deviation of the training data. So this is an example of the temperature attribute that has numeric values now. So we calculate, so instead of, so this is the way we calculate the likelihood of the class yes. So for a new evidence that has a temperature equals 66, then the density function of temperature equals 66 given the class yes is the following. And that's after we calculate the mean and the standard deviation. So the final value of the density function is this. So in the case of this new day or new evidence, we have the Outlook attribute as nominal type, the temperature attribute as numeric type, humidity is numeric, and windy is nominal. So the way we calculate the likelihood of yes is we apply the Bayes rule to get the probability for Outlook equals sunny, and the same for windy equal true. And when it comes to the numeric attributes, we calculate their corresponding density functions, and then we multiply everything with the prior knowledge to get the likelihood of the class. So what happens if we have missing values during training? Simple, again, way to deal with this when applying naive Bayes is to just not include them in the calculation of the mean and the standard deviation required to calculate the density function. So in sum, we just learned about naive Bayes, which is a simple probabilistic classifier, probability-based classifier that makes that naive assumption that all the attributes are equally important and they are independent. As we said, in real world, this does not apply. Most of the attributes are correlated. Some of the attributes may be correlated, so they're not independent. But even though this is the case, naive Bayes still surprisingly works well even with this assumption violated. Another problem is when we're talking about numeric attributes. So naive Bayes makes the assumption that those attributes are normally distributed, whereas in real world, many numeric attributes are not do not have a normal Gaussian distribution. So I recommend reading sections 4.1 for 1R and 4.2 for naive Bayes to deepen your knowledge and read in more details about these two algorithms. And then you, on your to-do list for this week, you have homework 1, which is 2 exercises related to 1R and naive Bayes.